Welcome back. This is Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch more. Today we're doing multivariable calculus. Chapter 2 is double and triple integrals. Today we're going to do double integrals over polar regions. From the pictures, you can see there's going to be fancy regions in the plane now that are arbitrary, and instead of viewing them as a one function below another function, it might be easier to rearrange these and view them with polar coordinates and integrate over polar rectangles instead of regular rectangles, and get the idea from Cartesian coordinates into polar coordinates, and it'll make some of these objects a whole lot easier to find areas and volumes if the regions look like these guys. Let's do that. All right, recall or call for the first time, or total recall, I guess. I don't know. Ideally, I think I'm going for total recall, or you just know what that means. Polar coordinates, which apparently you've done before. If you haven't, here it is again. I'm using a unit circle. Usually I call this one in our Cartesian coordinates. We focus on two pieces of information, x and y. Now what we're going to focus on is polar coordinates, and that is going to be the information r and theta. In the plane, if I know how far out I've gone, and I know how far around I've gone, I can find any point in space by saying, where's this? Oh, it would be that much angle and that radius. So you can find any point in space with these two pieces of information, same as you can find any point in space by going out this much on this one and this much on that one at a locate. This is what we're doing. And what we want to do is, if we change our functions from x and y Cartesian coordinates to polar coordinates, how does the double integral change, and how do the volumes of these regular rectangles transform into polar rectangles, and how is that going to work? And you're going to all be pirates, because it's going to be RD theta, not just dy dx, RD theta, RD theta. And then you're like pirates, and that's how you remember pirates, RD theta, always. Now that we have that one, we're going to switch in between. This is x and this is y, but in that right triangle, and using SOHCAHTOA, or the trigonometry of right triangles, I have that x over r is equal to cos theta, or solving for x is r cos theta. Similarly, y is r sine theta. And then converting, if you're practicing this, maybe you should go back and try to take something in Cartesian and put it in polar, and then put it in polar and go to Cartesian, so that you can recognize. You're hopefully familiar with some of the functions and what they look like in these ones, and now we've got more than one variable. And then we're going to put polar in there and spherical in this, and can you recognize what those look like and what are those curves? Doing that, these ones help us a lot. X squared plus y squared is r squared on the circle, and tan theta is y over x. Now let's look at double integrals over these polar regions. Blowing up one of these polar rectangles, we do the same thing we're going to do for a regular rectangle. We subdivide it into sub-rectangles by partitioning the r and partitioning the theta. And this is what it's going to look like. If we take now one of those sub-rectangles, sub-polar rectangles, and we pick a sample point in there, that should be orange, should be a j, ri theta j. And what we do is we pick an index to chop up the r, and then we pick an index j to chop up the thetas. Once we do that, we're going to have, at each one of these, we're technically going to have an ri and a theta j. But when we're actually looking at the change, we don't put the index in there. That's, each one of these is what we're saying is that delta r is this guy. Delta r is right there this time, again, same as the other one. It's just, and this is the delta theta that we're talking about. But this time, be careful. When we go to look at the area of that subpolar rectangle, we're going to get, because of, remember, the length of the arc subtended by angle in a circle of radius r is going to be r times that angle. In our little sub piece, that is r delta theta, not just delta theta times delta r. And then that's why we all become pirates. RD theta is coming from right here. So the area in each one of those, area Aij, is going to be equal to one of these sub-rectangles, but it's a polar rectangle, so we get r d theta, dr d theta, or delta theta, same thing. What does that do for us? Now we also remember that x is r cos theta and y is r sine theta. So our function at those points are going to become f of ri cos theta j, ri sine theta j. and then that's probably we're picking our sample points, and then you got to put your star on there, star, star, star. We're doing this at Riemann sums. This is just the polar coordinate version of that. Then what we're going to say is we have that times, we're going to have the double sum again from I equals 1 to m to j equals 1 to n of our two partitions, and that's going to be the approximate area of this polar rectangle. And then of course that has to be that times our area delta A. And then what is that going to give us? That's going to give us, long story short, that the double integral over this polar rectangle is going to be the double integral over R, this R now, a region of this type, of f of x, y, dA in polar coordinates is going to be the integral from alpha to beta. If you were going from your alpha to beta, and your R is going from A to B in general, the integral from A to B of now what? It's Fubini's, but it's polar coordinates now, and you're going to get f of R cos theta, R sine theta, and then now R dr d theta. There's like a half derivation of using Riemann sums to chop up that subrectangle and make the transformation. The key is you can sub in to change to f of xy to r theta. That's not a problem. This just becomes r cos theta and r sine theta. But the differential dx dy now became, remember, is going to be r dr d theta. That's the difference. There's a secret r in there. This will happen in spherical coordinates. Let's do an example. Example 1, compute the double integral over this region R of y dA, where R is now, we're going to change it. Now we don't have to worry about just type 1 and type 2 integrals. We can worry about polar coordinates. And it says we have the region bounded in the first quadrant by the circle x squared plus y squared equals 25. So let's draw an idea of what that's going to look like. First of all, here's the first quadrant. And again, this is the worst case scenarios where I'll try to be fairly specific about what they're actually saying about the region, but they hide it in the words, first of all. So we're in the first quadrant. This is quadrant 1, and it's saying it's bounded by, so it's going to be bounded by these guys, and who? The circle x squared plus y squared equals 5 squared. So that's going to take us to, where's 5? Right there, and right there, I guess, and right there. So 5. This is our region. R. What does that tell us? Once I have that, I can set up my bounds. This says that 0 is less than or equal to R is less than or equal to 5. And also 0 is less than or equal to theta is less than or equal to pi over 2. This is 0. This is pi over 2. Remember, you have to start thinking in polar again. The coordinate axes are 0 pi over 2, pi, and 3 pi over 2. And then you have all the other ones. So where are they? They're hidden there. Now I have my bounds. I can use Fubini's theorem and iterate this integral in any either order I want. But classically, you have to be careful because we have to do r dr d theta. Always put the theta on the outside and the r on the inside. This tells us that also y is equal to r sine theta. I have to put that in there. That's my function. So that says, remember, f of xy is y, and that says f of r cos theta sine r sine theta is equal to r sine theta, just y. That's what our function looks like now. Therefore, the double integral over the region of y is equal to the integral from 0 to pi over 2, the integral from 0 to 5 of our function now, r sine theta, r dr d theta. This is the Jacobian. We'll see in the end of this chapter when we do change of variables. We can do a couple clever moves. Remember from the property, I think 4, or I don't know if I did this property in the videos, but I possibly do in my lectures most of the time. But if you have that your function is a function of r and a function of theta, you can separate the integrals and do them separately so you don't have to worry about that. Maybe I shouldn't do that for the first one, but you can do that. You can do it both ways. This is equal to, using one of the properties of double integrals, whether it's polar or not, I can write that. The variables are mixed, so this is r squared times sine theta. I can write that as sine theta d theta times the integral from 0 to 5 of r squared dr. Because they were functions of, I could separate them. Sometimes you can't. If you had like sine of r and theta, well then I can't separate them, so I wouldn't be able to do that. But here I can, and then sometimes that makes it a whole lot easier. Then you can separate and compute in separate ways. What does that now give me? That's going to give me the antiderivative of this is negative cos theta, evaluated from 0 to pi over 2. And then this is times, what do I get? 1/3 r cubed, evaluated from 0 to 5. Here, what am I going to get? I'm going to get negative cos of pi over 2 minus negative cos of 0 times 1/3 5 cubed, which is going to give me, this is 0 and this is 1, and so that is going to give me 125 over 3. Quickly, before we go to example 2, what I'm going to do is show you, if you're like, I didn't remember, I'm never going to remember to separate, and were you talking about? Well, don't do that then. Just stick to your guns, do the RDR first, and then do the d theta after. Let's do it the other way. You better get the same answer. We now know it should be 125 over 3, or I'm wrong. This equals the integral from 0 to pi over 2 sine theta times, we had r squared, so now I'm taking the derivative 1/2 r squared, evaluated from, or sorry, 1/3 r cubed, evaluated from 0 to 5 d theta. I took the antiderivative, I cleaned it up. I'm going to write that as r squared. I combine it in there. And then now once you've done that, if you don't want to separate, don't then. I took the antiderivative of r, I held theta constant. Now I do that, that is equal to the integral from 0 to pi over 2 of sine theta times 125 over 3 d theta, which is now going to equal 125 over 3 negative cos theta, evaluated from 0 to pi over 2, which is equal to 125 over 3. See, we just turned the horrible symbol into the number this time. That still is equal to the integral from 0 to 5 of r squared dr. It's just the number now. And then this is equal to, now what do I get? I'm going to get negative cos of pi over 2 plus cos of 0, which is, and this one is 1, so we get 125 over 3. Yay, same answer. All right, example 2. What we're going to do is find the volume of a solid bounded by the plane z equals 0 and the paraboloid z equals 1 minus x squared minus y squared. So again, what we can view is if we have a surface which is now conveniently has x squared and y squared, so I think polar coordinates, that's r squared, so it's 1 minus r squared in polar coordinates. If I can start seeing that, now what they're talking about is they want the volume of the object, and I'm going to have a paraboloid which starts at 1 and then opens downwards, and then it's going to intersect the z-axis in some surface, and it's probably going to be a circle. And so I want to use polar coordinates to do that, and that's sort of what I can see as a mathematician already. Let's flesh that out and try and remember what these look like, and then that's exactly what we're going to get. So if I have this, let me draw the surface first always. We just have a dumpling basically, or a gumdrop, and then in there I've got coordinate axes. Here's z and x and y, close enough. Now what we want, and this is the point what? 0, 0, 1, because this is the surface 1 minus x squared minus y squared. What I notice is z equals 1 minus x squared minus y squared intersects z equals 0. If this is equal to 0, I get intersect z equals 0 in the circle x squared plus y squared equals 1. And now we have to just practice saying, okay, well what that gave me was the unit circle. This is my region R now, which is now a polar rectangle. I know that seems like a jumbo shrimp. It's like, well, maybe you should have thought of a different name. Oh. Anyways, this is our polar rectangle. And what does that say? In our polar bounds, this is going to give me 0 is less than or equal to r is less than or equal to 1, and 0 is less than or equal to theta is less than or equal to 2 pi. I know, my 0 looks like theta. 0. 0, empty set, theta. Now what do? I'm going to integrate that thing. This says that the volume above this surface, and this is z equals 0, the plane, xy plane. The volume above this surface, or below this surface and above z equals 0 is now equal to the volume below this surface and above this circle. That means in polar coordinates we have this bounds for our region, and the volume that they asked for is going to be the double integral over our region of who? 1 minus x squared minus y squared dA. I now turn that and phrase that into polar coordinates. That will equal the integral from 0 to 2 pi, the integral from 0 to 1 of 1 minus r squared, x squared plus y squared equals r squared, minus minus, times, careful, r dr d theta. Now what do? This is equal to, I can notice again, let's notice that. This is the integral from 0 to 2 pi d theta times the integral from 0 to 1 of r minus r cubed dr. I can split the integrals because I can separate, there's no theta, and I have iterated integrals. This gives me here, I like doing that because the theta is often quite nice and easy. This just gives me theta, technically evaluated from 0 to 2 pi, and this is going to give me 1/2 r squared minus 1/4 r to the 4 evaluated from 0 to 1, which gives me 2 pi minus 0 times, or 1/2 1 squared minus 1/4 1 to the 4 minus 0, which is 1/2 minus 1/4, which is 2 minus 1 over 4, which is 1/4. So 2 pi times 1 over 4, which is pi over 2. Now let's do that for a more general region where we can make r a function of theta. For a more general polar region, what we're going to do is, now as we change from an angle theta equals alpha to theta equals beta, as the angle changes, the radius is now changing on both ends. And those become functions of theta, therefore, and we're going to call the first radius h1 of theta and h2 of theta, just like we did for y as a function g1 of x and g2 of x in this business. This means that we can describe a more general region this way. The angle still goes between two constants, but now, just like the Fubini's theorem for the x and y, we now have r has functions of the other variable in its limits, and so we have to integrate that one first and use the stronger version of Fubini's theorem, and that tells us that the double integral, and notice also I use the notation r and d just like I did in rectilinear or Cartesian. R is a rectangle, d is a general region, r is now a polar region, or a general, d is now a general polar region. Either way, doing that, if I take the double integral over d of a function f of x, y, dA, this can now be equal to the integral from alpha to beta, the integral from h1 of theta, h2 of theta, f of r cos theta, and r sine theta as the second coordinate, r dr d theta. This is how to do double integrals over general polar regions. Let's do an example of that. One of these days, one more try. All right. Oh, I need that one to sketch with. Stop throwing your pens around. I'm going to sketch with this one. What we're going to do now is we're going to remind us this is property 3, regardless of whether it's polar or not. If you have the double integral over d of 1 dA, that's the area of your region D. We're going to use that property now to find the area of this rose. You're like, what's this rose? Yeah, remember back in apparently one of your previous calculus classes you did polar curve and sketching polar curves. How do we sketch that guy? Do you remember? Let's draw it in green. It's a 3-leaf clover, so let's do green, or the rose. First of all, I need to sketch that guy. I have theta values, and I have r equals cos 3 theta values. How do you pick which nice values you want? I want values where cos is plus or minus 1 or 0 or nice integers, because there's a 3 in there. I know that that's going to happen at pi over 3's they'll cancel and give me negative ones over positive ones. And then also happen at pi over 6s, I'll get pi over 2s, which will give me zeros. Long story short, I'm going to do from 0, then I'm going to do pi over 6, then I'm going to do pi over 3, then I'm going to do pi over 2, then I'm going to do 2 pi over 3, then I'm going to do, yeah, you remember this game? Then we're going to do, what's the next one? 2 pi over 3, 5 pi over 6, and then pi, I think, is the last one I'm going to need. That'll give me what I want. Now I start asking myself, this is back like if I didn't know what x squared looked like. I have to plot points to make sure it looks like a u. Then once I have these values, now what is that? I put that in there. I'm going to get r equals cos of 0, which is 1. Then that gives me the point, technically, see, theta is, I'm sketching this as a plotting theta against r is what we're doing. So then I'm going to get the point 0, 1. Then at pi over 6, see, I get 3 pi over 6, which is actually pi over 2, so I'm going to get 0. And then at pi over 3, I'm going to get pi over 3 times 3, which is pi, and so I'm going to get cos of pi, which is negative 1. And so I won't write out all the points, but you see where I'm getting at. Then I'm going to get at pi over 2, that gives me 3 pi over 2, so I get 0 again. Then at 2 pi over 3, that gives me 2 pi, so I'm going to get 1. And then at 5 pi over 6, that's going to be 5 pi over 2, which is going to give me 0. And then at pi, that's going to give me 3 pi, which is going to be negative 1. The negatives are the really mean ones where it's like, what do? The radius can't be negative. So you have to flip the quadrant you're in to sketch this. Oh, now what do we do? Yeah, exactly. This is just to get the region. Then we'll do the double integral over this. Let's draw just a baby one right here. Then what I need is, I need these guys, pi over 6. And then I needed pi over 3. Pi over 2 is this one. And then I need 2 pi over 3. And then I need 5 pi over 6. And then pi. And so then those are now there are these guys starting at 0 to pi. So now what we're saying is, to draw this, I draw my radius, and then what you do is, if you have, and you're doing a more complicated one, if you have different fractions like a 3/2 and a 1/2, and in there, and on your scale now in radius of those, you draw those. In ours we have a radius 1, so I want to do 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And then our radius is going to flip from 1 to 0 to negative 1, or back and forth from 0 and 1 in between these angles. How do you do that? What? Now I start at 0. When theta goes from 0 to pi over 6, my radius moves from 1 to 0. Now, though, careful, between pi over 6 and pi over 3, my radius goes from 0 to negative 1, but that can't be, so I'm going to flip quadrants. It's going to do it here. And then in this quadrant, from here to here, I go from 0 to negative 1, and that can't be. So I have to go, or sort of negative 1 to 0, it has to flip again, and I flip into this quadrant is where I draw it. I know. And then now I'm back to 0. From pi over 2 to, from here, in this one, I'm going to go from 0 to 1, so then you actually do draw it from here to here again. Then from 2 pi over 3 to 5 pi over 6, I go from 1 to 0, so I will draw the last loop into there. And then from 5 pi over 6 to here, in here, I go from 0 to negative 1, and that can't be, it has to go into this quadrant, so I am going to go like this, and we get the 3-leaf clover, or the TNA 3-leaf clover. Now what I want is, what do I want? I want the area of that 3-leaf clover. Look at the Irish. There. We're going to need to look at the iris to sketch or find the area now. Luckily, I can use double integrals, and this is the machinery. How do I phrase that? Where am I going to go from? Once I have this region D that we've sketched now I can compute the area of that. Of course, I'm a mathematician, so I'm going to use symmetry immediately, and I'm going to do it 3 times that, and we're going to compute one of the petals or one of the leaves, and we'll multiply by 3 to get the total area. So the area of the 3-leaf clover, which you now know how to trace out, it goes this way, then this way, then this way, then this way, and then back to this one. That's how you do that, the trefoil knot. This is equal to 3 times the area of just this one, which using syncopated algebra now is going to be the double integral over that region D of 1. We have to find our bounds. Finding our bounds of that just one petal, I'm going to be lazy and go from negative pi over 6 to pi over 6. And that's going to give me negative pi over 6 is less than or equal to theta is less than or equal to pi over 6. And r is going from where? 0 is less than or equal to r is less than or equal to cos theta this time. So the difference now is we cos 3 theta. Gotcha. We don't have just bounds or constants in both of our bounds. R can be functions of theta now. And therefore, this double integral is going to be equal to the integral from negative pi over 6 to pi over 6 times, or the integral from 0 to cos 3 theta. And then what do we have? Just 1, but remember we get r d theta. That is equal to the integral. First of all, I'm going to use symmetry. Well, I'll do the move first. This is the integral from negative pi over 6 to pi over 6 of 1/2 r squared evaluated from 0 to cos 3 theta d theta, which is equal to the integral from negative pi over 6 to pi over 6 1/2 cos squared 3 theta d theta. Now what I can see is this is an even function, and I'm going from negative a to a, so I can double the integral and make that from 0 to pi over 6 because this is an even function in theta. So I'm going to move that up. Calculating that is going to be what? Oh, and this should say, there should be a 3 in there the whole time, technically, if we're computing the total area. So what does that give us? That tells us the area of one of those guys is equal to 2 times the integral from 0 to pi over 6 of 1/2 cos squared 3 theta d theta was my point. So those 2's cancel. We'll remove the multiplying by 3 to get the total area in the end. This is now equal to, I have to use a trigonometric identity. That is 1/2 1 plus cos 6 theta, 3 times 2. So this is equal to the integral from 0 to pi over 2. That turned into a 2 also somehow. Pi over 6 of 1/2 1 plus cos 6 theta d theta. That is now equal to 1/2 theta plus 1 over 6 sine 6 theta, evaluated from 0 to pi over 6. If you notice, at 0, sine is 0. At pi over 6, I'm going to get 6 and 6 cancel, and I'll get sine of pi, which is also 0, so this is gone. And then at 0, obviously I'd have 0, so the only value I get is 1/2 times pi over 6, which is equal to pi over 12. Now, that was only one petal, don't forget. So the total area of this guy is equal to 3 times the area of one of those, which is 3 times pi over 12, which is pi over 4. Please subscribe right here, hit the notification bell. I'll see you next time.